Hey guys, so in this module, you are going to be going over the alternate form of the derivative, and then you're going to use that to help you figure out if a function is differentiable or if a function is not differentiable. And so this first part is just some quick notes on the alternate form of the derivative. Then we're going to do some practice. And then the second part will be on differentiability, and then you'll do some practice. And then there's some text with problems for you. All right, so we are talking about differentiability. And continuity. That's the overarching theme here. But in order to talk about that, we need a more efficient way to figure out the derivative of a function when we're evaluating it at a point. So just to recap, right now, if we want to find the derivative of a function at a point, we go through the limit process, right? We do the limit as h goes to 0 of that average rate of change, essentially, that secant line. F of x plus h, subtract f of x all over h. And by taking the limit as h goes to 0, we're now saying, well, now this is representing the instantaneous rate of change instead of the average rate of change. So again, by taking that limit as h goes to 0, we're now finding the instantaneous rate of change, which is also the derivative, which is also the slope of the tangent line when we evaluate it at a point. So we can just kind of skip, hop, jump right to the slope of the tangent line by using what we call the alternate form of the derivative. And again, this is used to evaluate a derivative. We'll say, yeah, evaluate the derivative at a given point. When given the original function. So we're going to be given the original f of x, and we're going to be able to both take the derivative and evaluate it within the same process, eliminating that extra step needing to substitute it. So the alternate form of a derivative says that f prime at some c value is equal to the limit as x goes to that c value of f of x subtract f of c all over x subtract c. So notice we're still taking the average rate of change. And then we're taking the limit as x goes to c. So again, we're still letting this denominator go to 0. So we're still letting that difference between my x values, that h that we called it with the definition of the derivative, we're still letting that go to 0, which is why it's giving us the instantaneous rate of change at a given point. Or this process will give us the slope of the tangent line at a given point. So what we have here is we have some function, and then we have a c value, and we have an x value. And so this value right here is f of c, and this value is f of x. And this looks really familiar. Before we had f of x plus h and f of x, right? And now what we're doing is we're this right here calculates the slope of this line. But what my limit does is it says, all right, let's bring this x value closer to the point where we want to know the instantaneous rate of change. So by letting x go to c, we're saying let's bring this as close as we possibly can until it's right on that point so that we can figure out what the slope of that tangent line is right there. All right, so let's see some of these in practice. And we're going to look at this from two different avenues. We're going to look at this from first, being given the limit as x goes to c of some function and figuring out what was the original function in there and at what value are we evaluating it. And then from there, we'll actually evaluate that limit just to get some practice in there. Oh, I lied. First, we're going to actually evaluate and then I'll do that. All right, so we want to, our directions for this would be something like determine f prime of 7. So this is my c value. That 7 is my c value. So what I'm going to do is I'm going to set it up. I'm going to say f prime 7. So again, this is my instantaneous rate of change when x equals 7. This is also my the slope of my tangent line. And this is my derivative evaluated when x equals 7. So my alternate form of the derivative says I'm going to do f of x, which is the square root of 3x. I'm going to do the limit as x goes to my c value, the point at which I'm evaluating this derivative, of f of x, so the square root of 3x, subtract the square root when I evaluate this function. So when I do f of 7, I get the square root of 21. So this is going to be the square root of 21 all over x subtract 7. Now I need to find a way to evaluate this so that I can substitute 7 into this. So let's go ahead. Our general rule of thumb here is to multiply by the conjugate, right? So let's follow that same process like we normally do. I'm going to multiply by the square root of 3x plus the square root of 21 in both my numerator and my denominator, just like we did with our definition of the derivative. I'm writing the limit process at each instance until I substitute in. This is forcing a difference of squares. Remember, that's why we do our difference quotient. That's why we do our multiply by our conjugate. So I have 3x subtract 21 all over x subtract 7 multiplied by the square root of 3x plus the square root of 21. Now notice I'm trying to get rid of this x subtract 7, right? Because then I can substitute 7 into this function or into this expression. So notice that if I factor out a 3 here, so I'm going to rewrite this. I can factor a 3 out of my numerator, and I'm left with 3 multiplied by x subtract 7 all over x subtract 7 multiplied by the square root of 3x plus the square root of 21. I now have these x subtract 7s that can cancel out. So that's gone and that's gone. And now what I'm left with is the limit as x goes to 7 of 3 over the square root of 3x plus the square root of 21. Well, now I can substitute in that 7. So I have 3 over the square root of 21 plus the square root of 21, which equals 3 over 2 root 21. If I were then asked to write the equation of the secant line, I have my ordered pair for my original function. My original ordered pair would be 7 square root 21. And I would say that my equation of the tangent line is y subtract the square root of 21 equal to 3 over 2 root 21. You can rationalize that, or you can just leave it like that. That's totally fine. X subtract 7. And that would be our equation of the tangent line. All right. So these are a few examples of first figuring out what even is my original function and then evaluating this derivative. So just good practices, or rather evaluating this limit. So to figure out what our original function is, if we see that this is in the form limit as x goes to c of f of x subtract f of c all over x subtract c, this first expression right here is going to be what f of x is. So we can say that f of x is 1 over the square root of x squared, my pen's going haywire, subtract 2x. And I'm finding the instantaneous rate of change of f of x when x equals this c value, so 7. For the next one, notice I'm evaluating it at x equals -2. My original function is 3x subtract 9x squared. And I just want to verify real quick. This one was pretty straightforward because you can't really do much manipulation. But I'm just going to come down here real quick and make sure that I get out a 42 to make sure there's no other part of this polynomial that I'm missing. So if I do 3 multiplied by -2, subtract 9 multiplied by -2 squared, I get a -6 subtract 9 multiplied by 4, which gives me -6 subtract 36, which gives me a -42. Normally with the alternate form of the derivative, I would expect a subtraction in here, right in here, but notice this addition. So I just wanted to verify that it was in fact a -42 as my output, which is what forced that to be a positive. I always want to just do double checks. And in this case, we're finding the instantaneous rate of change when x equals -2. All right, last but not least, we have the limit as h goes to, so we have our function is 3 times the natural log of 2 plus some h. So notice, let me back up, sorry, fell into my own trap. This function is asking us, notice it has the limit as h goes to 0, and it's 3 ln 2 plus h, subtract 3 ln 2 all over h. So notice this isn't the alternate form of my derivative, this is the actual form of my derivative. So let's just back up for a second here. We have the limit as h goes to 0. This should be f of x plus h. Subtract whatever f of x is all over 2, right? Or rather all over h. Notice here that I don't have an x term in here, and I don't even have an x term in here. So my original function is simply 3 natural log of 2. So my original function in this case is 3 times the natural log of 2. And it says instantaneous rate of change at x equals, x. Oh, my apologies. Let me back up. 3 ln x. We're evaluating this function when x equals 2, because notice where the x would be is where the 2 is. So that's being evaluated when x equals 2. So this would be 3 ln x, and we've now replaced that with a 2 because we're evaluating it when x equals 2. So that one's kind of like a hybrid between my derivative and the definition of the derivative and the alternate form. All right, let's clear. All right, so hopefully you've tried this problem. We're given f of x equal to 1 over 5x, and we are evaluating when x equals -2. So we're finding the derivative of the function when x equals -2. So I'm saying f prime of -2 equals, and I'm going to use the alternate form, the limit as x goes to -2. And then I have f of x, so 1 over 5x, subtract. Let me go ahead and find out what f of -2 equals. Well, f of -2 is a -1/10. So I'm subtracting a -1/10 all over x, subtract a -2, so x plus 2. I'm going to keep cruising. I see that I have a complex fraction here. So I'm going to go ahead and multiply by 10x over 10x, because that would be the common denominator. And I just want to eliminate these denominators out of the numerator completely. So when I multiply 10x by 1 over 5x, the x's will cancel. I'll be left with just 2. And then when I multiply 10x times 1 over 10x, I'll just get x all over x plus 2 multiplied by 10x. And now I have x plus 2 and 2 plus x, so those cancel. I'm left with the limit as x goes to -2 of 1 over 10x, which is a -1 over 20. So this would be the slope of the tangent line when x equals -2 for this function. This would be my instantaneous rate of change at x equals -2. And this is the derivative of f of x evaluated at x equals -2. If I were to write the slope of the, if I were to write the equation of the tangent line, I would say I have y, and this is my output, plus 1/10 equals -1/20th x. My input was -2, so x plus 2. So that would be the slope of my tangent line at that point. I'm sorry, that would be the equation of the tangent line at that point. All right, last problem here. We have the limit as x goes to pi over 2. So identify this as being in the alternate form of the derivative. And so my f of x function is this function right here. So it's going to be 6x squared multiplied by the sine of x. And I'm evaluating it at pi over 2. And that's it. We could go through and simplify that down and figure out what that is. Actually, let's do that just because it's a trig function, just so you can see that done out. So we have the limit as x goes to pi over 2 of 6x squared sine of x, subtract 3 pi squared all over 2, all over x subtract pi over 2. Actually, let's just leave that alone.